I got to look at a couple more of these optimization problems. Okay, so here's one. It's one of the ones in your book there. Okay, it's the issue is this. Okay, we have the point here at 4, 0, and that point is fixed as point B, and we have a point here A on the line y equals 3x plus 1. Okay, so we want to find the minimal distance from the point B to the line. Okay, so I've done this up in Sketchpad so you can see. Here's the distance AB. Okay, and here's the A. Okay, and the question is here, more specifically, find the coordinates of the point on the line closest to 4, 0. So, you know, we move that along, and we're seeing the distance getting smaller and smaller, and right about here, it's at its smallest value, right? Okay, um, so we want to know what are the coordinates of that, and it looks like we can find those coordinates right there. We actually did this problem with coordinate geometry before because the shortest distance um, along from a point to a line involved finding the perpendicular bisector, the point of intersection, and then computing the distance AB. So it's a very detailed problem earlier, if you remember. With functions now and optimizing it, it will prove to be a lot easier. So we'll see here's the shortest distance, but let's look at how we find that. So it is a distance problem, so it's going to entail the distance formula. And it's going to involve the quadratic, it's going to be a quasi-quadratic function, as we'll see. So this is instructing us on what we can do. We can drag point A, and so we want to find a distance as a function of the x coordinate of this point A. So determine the value of x for which AB is at its smallest is the task at hand. So here's what I'm asking you to do is say a little hint. Express the y coordinate of point B, of point A, as a function of x. Well, since the point A is on the line 3x plus 1, then rather than call the point here at A x comma y, I'm going to call it x comma 3x plus 1. So the coordinates of that point, uh, regardless of where that point is, at that point, anywhere on that line will have coordinates x 3x plus 1. Okay? So knowing that they are the coordinates of that point, whether it's here or at the minimal distance, is valuable, and we need to call upon that. Our other point 4, 0 is fixed, so we're going to compute the distance. So apply the distance formula between the general expression of this point, okay, and the point 4, 0. So here it is, x minus the x coordinate of 4, and y minus the y coordinate of 0. But y is 3x plus 1. So here you can see is the the uh, the distance as a function of x. That's expressing the distance as a function of x, okay? And you can see that when you expand that out, it's going to be quadratic underneath the radical sign, which makes that quasi-quadratic. And okay, the x value that minimizes the quadratic will minimize the distance, okay? So well, that's what you want to do. Express this as a quadratic, ax squared plus bx plus c, and use the negative b over 2a to find the value of x for which this distance is at a minimum. Okay. Got one other problem I want to look at. Okay. So let's go back to this PowerPoint presentation and look at this last problem I forgot to get to on the previous one. Okay. So uh, actually, that's not one I want to look at any rate because it's just a follow-up on this optimization problem. I have one other optimization problem that I've illustrated here with the sketchpad. Let me pull that one up, okay? So I'm going to open that one and forget where that was, but let's see. Uh, okay, bear with me here. It's coming. It's coming. Rectangle and a circle. We saw that, okay? And the other one is the diagonal, a diagonal problem. that I have. I don't see it. I don't see it. Okay. Shortest distance to a line. That's the one we just did. I'm sorry. That'll do it for now. Okay. Sorry for all that bantering on like that, but I'm not finding it, so we're not gonna banter any longer. That's the end of this video. Don't forget quasi-quadratic. Okay.